In this lesson, we shall focus on mathematics, right? Calculus in higher dimensions. We're looking at MAT2615. And we're looking at the kinds of questions that must be learned for examination purposes. And this is not at all different, right? We're looking at question 4, right? And this question 4 it's actually a carefully selected question, a popular question in the past years. Consider the R2 to R function f defined by f of x and y, which equals x squared minus 2xy plus y squared. Let V be the plane that is tangent to the graph of f at the point xyz equals 1, minus 1, and 4. Find a vector that is perpendicular to the plane. Find a vector that is perpendicular to the plane. The question is, how do we do this question? How do we find a vector that is perpendicular to the plane V? Because V is actually a plane that is tangent to the graph of f at the point 1, minus 1, and 4. For 4 marks, we need to find a vector that is perpendicular to the plane or a vector that is orthogonal to the plane. And to do that, we use the derivative. So we're going to do the question 4a. And we let, right, and so we let the following. So to find a vector that is perpendicular to the plane, we actually consider, let's first start by considering the following. Let us start by considering the following. So first things first, we would like to then say, let us consider first. Consider. Right, so consider the function f, which is a function of two variables, and we call it x squared minus 2xy plus y squared. Okay, and let g of x, y, z, which is the same as the following. So we introduce a new function. We call g of 3 variables. And it is going to be the function f, x, and y minus the variable z. And by dint of this, this means that our function g of x, y, z is the function f, which is x squared minus 2xy plus y squared minus z. And upon careful examination, we have exactly the following. We, moreover, are able to note that the gradient of the function g is a vector, is normal to the graph right, it's normal to the graph of f. And at this point, we can be able to find the gradient of the function g, and g is a function of 3 variables, x, y, and z. And the gradient of g can be actually also seen as the following. We can write the gradient of g as the gradient of the function g. And as a consequence, this gradient of g can be seen as gx, gy, partial z, which means the gradient of the function g so you differentiate g with respect to x. And if you do, with respect to x, the derivative of x squared becomes 2x. The derivative of minus 2xy is minus 2y with respect to x. And the partial derivatives of y squared and minus z are simultaneously 0, both. gy is the partial derivative of the function g with respect to the variable y. And now the derivative of g here becomes 0. The derivative of, the derivative of x squared with respect to y is 0. And the derivative of minus 2xy with respect to y is negative 2x. With respect to y, the y squared has the derivative 2y. Next. Now we next computer, because we want to find a vector that is perpendicular to the plane. The question is, how do we find a vector perpendicular to the plane? If you have been given that this plane, the plane that is tangent to the graph of f at this point, it is tangent to the graph of f at this point. A vector.
I'm sorry, can I please disturb you?
Yes, please.
My network wasn't working, but I don't understand why you introduced the new G.
Yeah, the new function G.
Yes, and why are we doing what's this derivative of G?
The gradient of G.
And yes, why?
Good, right. It is a okay. First, we introduce G because we have been given a function f of 2 variables. Right, of 2 variables, and these variables x and y. Those are the 2 variables of x, which are x and y. So that then in the end, we have the following. Right, so now, okay, we have a function of 2 variables. This is very important. So if this function is a function of 2 variables, we introduce another function g, and this g is of 3 variables. Because the point is actually an order triple. Because you are told that let V be the plane that is tangent to the graph of f at the point. So this plane is tangent to the graph of f at the point. As a consequence, then what we're then having is that also this function here is a paraboloid. Because if you look at it very carefully, you have the function f, but the function f of x and y is x minus y squared. X minus y squared, which is exactly this. So this one qualifies to be called a paraboloid. Introducing this means that this function, which is a paraboloid, is f, but it is also z. So we have variables 1, 2, 3. So the points must be 3 variable points. But the g now, the f is 2 variables, so we must introduce a third variable, and you always introduce a minus z. Right, so that we form g, and the g is a function of x, y, and z, and this is f of x and y minus z. And now then we formed a new function g, which is an order triple. Right, now the gradient of g is normal to the graph of f. So the gradient of g, x, y, z is this, which is gx, gy, gz. Right, with the gradient is also written as the del of g, like del. So now we're dealing with the del of g. Okay, now we're finding here the gz. You find that the derivative of this with respect to z, 0. This term with respect to z, 0. The derivative of y squared with respect to z, 0. The derivative of minus z with respect to z becomes a negative 1, like so. This is actually what we have got. And so we can continue then and say, therefore, the gradient of G1 minus 1, 4. One minus one, 4. So you put, so it's going to be 2. X is 1. Y is minus 1. X is 1. Y is minus 1. So that this in the end it becomes 2 plus 2, which is 4. Minus 2, which is minus 4. And then minus 1. And this therefore means the gradient, the vector that is perpendicular to the plane V is this one. So the gradient of a function produces a vector that is perpendicular to the plane that is tangent to the graph. So now this paraboloid is a paraboloid of minimum vertex like this. If it's a paraboloid of minimum vertex this way, and you can draw a tangent plane to it. So if there is a tangent plane to it, like this, okay, so okay, this is the plane. A plane is a two-dimensional formation. It is tangent to the paraboloid, and we want to find a vector that is it is tangent and it touches at one point, 1 minus 1, 4, and this is the plane, like so. Then we're asking the question, find a vector that is what? Perpendicular to this plane. This plane is tangent to this. To find a vector that is perpendicular to the plane, you need to find the gradient. This gradient function, which is the derivative of the function, right? It's able to produce a vector that is perpendicular to the plane. A vector that is perpendicular to the plane. Any question on this one? So this is the vector. This is the vector that we have got. This one is the vector. This one is the vector. Right, so now we have solved question A. This question is very popular. That is why we are doing it here. It's very popular. That is why we're doing it, because it is so popular. Very, very popular. So it's the kind of question that you must take note of. You must take note of. Right.
Okay.
We move on. Next, we need to find an equation for the plane V. How do we find an equation for the plane V? Right. So now, right. So we continue. Because we
Yes.
just, yes, we used del of G. But del of G is also called, it's also written like this. And it is also called, nabla. Right, so it would be nabla of G. So this would be nabla. Nabla of G. Okay, now at this point, to find to answer the question B, to find an equation for the plane, we're gonna use the formula that is very famous. So we use x dot n is equal to p dot n. This is the formula that we learn, and it is a very important formula that must be understood. So now this formula here allows us to take an arbitrary vector x with the coordinates x, y, z, like this, times minus that. We take a point. This is the point. 1 minus 1, 4. Dot 4 minus 1. 4x minus 4y, which is 4 plus 4 minus 4. Minus z. 4 minus 4 is 0, and then you are left with only what? We're left with only 4. And this is the equation for the plane. So to find the equation of a plane, we use this formula, xn equals pn. Right, vector x dot vector n, which is the normal vector. So now we note that this n is called the normal vector. Simultaneously, we know that this one here denotes the x dot n equals p dot n is called the equation. It's the formula for finding the equation. The equation of a plane. Right, it's the formula for finding the equation of a what? The equation of a plane. So we have answered the question that said, find an equation for the plane. This is the equation of a plane. How do you find the equation of a plane? We use x dot n. This is the dot product, right? And so now, if you say two vectors, you take the dot product, you take the point vector, and then you dot it with n, and then this becomes what we call component multiplication. So that you have, if this vector dot this one, the vector x dot the normal, it's going to be x times 4, which is 4x. And then y times minus 4 is minus 4y. Z times minus 1 is this. And then we have 1 times 4, which gives us a 4, minus 1 times minus 4, giving us a 4. 4 times minus 1 gives us actually a minus 4. And then we simplify everything, get to this. And this is the answer. This is the answer. This becomes the answer. We move on to the next question. We proceed to the next question. Right. We proceed to the next question.
Yes, yes.
All right, good. In the next question, we're going to tackle question C that says, find an equation for the line. How do we find an equation for the line? That contains the point 1 and 1 minus 1, 4. And is perpendicular to the plane V. Let us continue to check this out. Let us continue and check this out. So now, in checking this out, the couple of things that we need to do here. Right, and we need to check the following and make sure that everything is well and very much okay. So, to find the equation of a line, we actually do the following. We say such a line, that is what we write first. Such a line, right, such a line is parallel to, right, because it is perpendicular to the plane. If I find an equation for the line L that contains the point and is perpendicular to the plane, perpendicular to the plane, it means it's parallel to the normal. Perpendicular to the plane implies that it is parallel to the normal. It's parallel to 4 minus that. So its equation is XYZ. So it contains the point, this, plus T, which is, if it contains the point, you put this point first. And because it's parallel to the normal we got it in the previous question, which is 4 minus 1. And then T is our parameter, and T is an element of the set of what? Of real numbers. Okay, but now we can simplify this thing. So this is the answer. If you don't write the answer like this, you say or. Or X, Y, Z. You can multiply 1 minus 1, 4 plus, then you have 4t minus 4t minus t. So you can multiply everything like this. And then this one here is going to become XYZ. One plus 4t minus 1 minus 4t. 4 minus t. T is R. Which means that you can say the equation of the line is given as these particular parametric equations. And the parametric equations are as follows. They are as follows. Which means that x of t is the same as 1 plus 4t. Y of t is minus 1 minus 4t. Z of t is 4 minus t. And t is an element of the set of real numbers. So to find the equation of a line, this is what we do. This is exactly what we do. So we put a point t into the parallel vector. So you have 1 minus 1, 4. Right, so XYZ, which is 1 plus 4t minus 1 minus 4t, 4 minus t. X is 1 plus 4t. Y is minus 1 minus 4t. Z is 4 minus t. T is an element of R. Okay, yeah, so that would be... Okay, that is the equation for the line L. And this equation of the line L, it contains the point 1 minus 1, 4. So you put the point here, plus the parameter t times the normal, times the vector parallel to the line. So this vector, it's a vector that is parallel to the line. Parallel to the line. It's a vector that is parallel to the line. This is the answer. Think about it.
Okay.
Yeah, make sure you understand how to find the equation of a line. To find the equation of a line, you need two things. You need a point through which the line passes, because this line contains the point 1 minus 1, 4. But it is also parallel to this vector, because we've been given something here. We've been given a paraboloid. This paraboloid has a plane, right? And this plane is tangent to this at a point. Okay. Okay. Now look, if this plane is tangent to this, then we used the grade to obtain a normal to a vector that is perpendicular to this plane. And now, if we're told that the equation of the line that contains a point is perpendicular to the plane, so a line that is going to be perpendicular to the plane is going to be like the normal, because they are both perpendicular. So that this line and the normal are parallel because they are both perpendicular to the plane. So to find the equation, we need one vector that is parallel to the line, which is the normal. And the equation of the normal vector is 4 minus 4 minus 1. And then this particular normal vector, this particular line, passes through 1 minus 1, 4. Passes through 1 minus 1, 4. So we continue.
Yes.
Right, we continue. And then we look at the next question. We look at the next question. Right, so now, okay, yeah, there are other things I want us to discuss. There are tons of questions, shall give you homeworks as well, and many other things. I want us to spend some time on these kinds of questions. I want us to spend some time on these kinds of questions. Let D be the region in R3 below the plane Z equals 2 and above the surface x squared plus y squared minus 2. This x squared plus y squared minus 2 is a paraboloid. This one is a paraboloid. It's a parabola in 3 dimensions. Make a 3-dimensional sketch of D. Let us look at how we can do this one. Make a 3-dimensional sketch of D. Right, so we continue with our investigation.
Yes.
We continue with our investigation, right? So what we're going to look at right now is how to make it the 3-dimensional sketch. Let us make it this 3-dimensional sketch, right? So in making the 3-dimensional sketch, there are a couple of things that we need to take into account, because we want to understand planes, but also we want to understand normal vectors. Right, we want to understand normal vectors. Okay, so we're continuing, please. We are going
Yes.
on. Yeah, we are going on with this question. Very interesting, but we want to sketch first. So in sketching, we will focus on the particular things. The following things are important.
Can you please explain what makes this surface equation a paraboloid? Like, how can I see whether it's a
Yes, a
paraboloid or
paraboloid or not, right? Because it is from high school, there's something called a parabola. Because we see degree 2, y equals x squared. Or you can see y equals ax squared plus bx plus c. Okay, this one is called a parabola. Right, so now then there is, if it is z equals x squared, it's because obviously you are dealing with z. Right, you're dealing with that. So z equals x squared, for instance, it's a paraboloid that is such that it is a in the zx, or you can say xz plane. Right. So in the xz plane, what do? You remove something. You can remove y. Okay, you remove y, and then you are left with these. So you can extend z like this. You can extend x like this, for example. And then now your z equals x squared, meaning that z is going to be positive. So this is the kind of graph. So this is going to be the parabola that is going to be in the xz plane. But now, because these things are in 3 dimensions, you call it a paraboloid. But this 3-dimensional plane has been built with great ingenuity and creativity. Because now it is a combination of one orthogonal axis called the y-axis that is perpendicular to the x and the y-axis they combined. Paraboloid is seen by the degree 2 in the same way that a parabola is y equals x squared plus bx plus c, and then we have a quadratic formula that we use to solve this one. B squared minus 4ac all over 2a. Make a 3-dimensional sketch of D. Right, make a 3-dimensional sketch of D. We shall make the sketches. We are making the sketches here. Right, so as we are making this particular sketch, I want us to focus on some stuff that becomes so important. Some stuff that becomes extremely important. Right, the question is, how do we sketch this here? How do we sketch? Okay, the way we sketch a parabola, we x and y, then we do this. Then that is the parabola, like y equals x squared. Right. So now let us look at 4.1. So to sketch a parabola, this is in 3 dimensions. So we're going to have this. ZYX. Right. So, well, now, obviously, if we look at the equation, Z is y squared, x squared minus 2. So when these are both 0, then Z is minus 2. So which means that we're going to have the following. So you're going to sketch like this. And then you're also going to sketch like this. Right. So this is the situation. But now at the point that, so it becomes this one whose equation is Z equals x squared plus y squared minus 2. Okay, but whenever Z equals 2, then you're going to have Z is x squared plus y squared minus 2. But if z is 2, then it's going to be x squared plus y squared minus 2, which means that 4 is x squared plus y squared. Okay. And this means that there is another curve, x squared plus y squared equals 2 squared. So which means that at this point, whenever z is 2, then this thing becomes a circle. Because x squared plus y squared is equal to 2 squared. It's a circle. It's a circle center, 0, 0 radius. Radius r equals 2. Radius r equals 2. Radius r equals 2. Radius r equals 2. So this is it. We've made a three-dimensional sketch, and this is enough. So this three-dimensional sketch, you can see it like this, or it's like a vase. It's like a vase or a vase. Okay. Now the question is, what is the right pronunciation? Okay. Normally vase is the pronunciation, but it looks like this, like a jar, like a jar. Okay. So we have sketched this one, and it is called a paraboloid. Paraboloid. So now the couple of features of the paraboloid we did not spend a lot of time on, like in the xy plane, to sketch this, z becomes 0. Z becomes 0, which means that whenever z is 0, 0 is x squared plus y squared minus 2. Which means, therefore, you have x squared plus y squared equals 2. Which means that at this pointer, you're going to have a situation where this thing becomes like a circle here. But it becomes a circle when this is equal to 2, then you can put the square and square everything. Because for us, the circles from high school, they're x squared plus y squared is equal to radius squared. Meaning that obviously you're going to have the square root of 2 there. All right, but now this would be just the description of our paraboloid. And then we proceed to the next question. In the next question, we can express the volume of D in the triple integral using cylindrical coordinates. Let's look at that one. Cylindrical coordinates. Now, cylindrical coordinates focus on the fact that if you have a three-dimensional setup, Z, Y, X, and then you have this. And then you have minus 2, 2. Now, express the volume of D as a triple integral using cylindrical coordinates. There is in 4.2, you have D for the cylindrical coordinates. We use R theta Z for what we call cylindrical coordinates. Cylindrical coordinates. So that 0 is less equal to theta less than 2 pi. 0 is less equal to theta less than 2 pi. And then 0 is less or equal to R. Okay, because now the R theta, it's the radius we were talking about. Right, becomes a radius we were talking about there. So you're going to have that the radius we're talking about is between 0 and 2. Between 0 and 2. In view of something called the XY projection, we're going to discuss the XY projection, which is a projection of this in the XY plane. Because if you look at the image of this,
I get
it becomes here. It is here. And this one is x squared plus y squared is equal to 2 squared. Is equal to 2 squared. Right. So we know that. Why is it 2 squared? Because you have the plane z equals 2. The plane z equals 2 is this one. But you see, if ever the paraboloid and the paraboloid and this plane are equal, so the plane is z equals 2, yet the paraboloid is what? Is x squared plus y squared minus 2, which means 2 is x squared plus y squared minus 2, which means that x squared plus y squared equals 4. Right, and this is like 2 squared, which is giving us the radius that, looking at something called the XY projection. XY projection. All right. Now, we continue. We need to find the Z limits of integration, which means it's going to be R squared minus 2. Less or equal to Z, less or equal to 2. Therefore, the volume
Can
is,
you please explain? Sorry, can you please explain the z interval, like the r squared minus 2y?
okay, yeah, the V interval, yeah? Okay, good. And now,
I mean z, not v, z.
okay,
Z.
interval, yeah. Okay, good. Yes, let's discuss it. Let's discuss it. Okay, now the couple of things that remain very important, because whenever the Z is written like this, you'd have that Z is this. So you have Z, we have Z equals 2 here, for example. See, Z equals 2, but x squared plus y squared is equal to what? X squared plus y squared is r squared minus 2. And the r squared minus 2 would give the equation of the paraboloid in polar coordinates. In what we call polar coordinates. And obviously, these polar coordinates are called cylindrical coordinates in this case.
I don't understand how z becomes rx squared minus 2.
Yes. Because what is x squared plus y squared? Is equal to r squared. So wherever is x squared plus y squared at any random point, x squared plus y squared is equal to r squared when you're doing cylindrical what? Cylindrical coordinates. Okay. So now with these then, we have z. What is z equal to? Here. We can see that z here is x squared plus y squared minus 2. What is x squared plus y squared? It's r squared minus 2. R squared minus 2. That is why it becomes r squared minus 2. But now let us analyze these together. So it is the paraboloid. The paraboloid is the equation z equals r squared minus 2. Okay. So it is that, so it means that z is r squared minus 2. That is this one. Okay. So now you need to express the volume of D as a triple integral. The equation of this is x squared plus y squared minus 2, but x squared plus y squared is r squared, because this is the equation of a circle, so that z is r squared minus 2. This is the equation. But when you're looking at the z coordinates, Right, let's look at the coordinates of Z, which means that we're going to have a couple of things here. Z increases upwards from the origin 0, 0, 0. Z increases upwards. So that now we actually will understand that Z at any point, if you just draw a line like this, or a line on the side like this, it's going to pass through the boundary in the increasing Z direction, which is the upward direction, which means that Z at this point is going to stop at this point at the top point, which is Z equals 2, which is the plane Z equals 2, which is the cover of this paraboloid. So that Z is going to be at any point R squared minus 2 is less or equal to Z. But the highest point of Z is Z equals 2. Z equals 2, which is the top part of the what? Top part of the plane. So that now using cylindrical coordinates, we're able to do the following. So therefore the volume is the triple integral which is the integral. Right, the integral now is going to be given in terms of 3 triple integral. Volume is always r dz dr d theta in terms of what? Cylindrical coordinates. Then you have the theta, which is a full revolution, which is 0 to 2 pi radians. The radius of this circle at the top, we said already it is x squared plus y squared is equal to 4. Whenever you equate, you make the plane, you make the plane equal to the paraboloid. The plane at the top is z equals 2, this plane. And this plane is like what? It's like this. Like a two-dimensional piece of paper that you have put to cover this. So we then can see that, okay, the plane is z equals 2. The paraboloid is x squared plus y squared minus 2. Then if this plane and the paraboloid are equal, which means x squared plus y squared minus 2 is equal to 2. With this in mind, it means x squared plus y squared is equal to 4. But 4 is 2 squared. And this gives us the radius of this particular circle, whose xy projection at the top, you have x squared plus y squared is equal to 4. But if you project it, you squash it, you force it down, you look at its shadow, which is the xy projection, on the xy plane. X-axis, y-axis, they form the xy plane. If you imagine z removed, the perpendicular axis removed. Okay, now with that mentioned, we're able to say the following, yeah? Which means, therefore, the radius is 0 to 2. The z is r squared minus 2 to 2. Like that. Exactly like that. But now they said do not evaluate the integral. Just write it like this. Just write it exactly that way.
So if they say you don't have to evaluate the integral, it means you don't have to transform that x squared, like equated to the, I don't know what is the coordinates, but saying that x equals to r
Numbers, yes, whatever
cos,
numbers, yes, etc.
yeah,
Yeah, well, I mean, do not evaluate means that stop here, don't calculate don't integrate this, because you would integrate this, like with respect to z, you would have to find the integral. You'd have to integrate and substitute the limits of integration here. But they're saying don't do it.
all right,
Yes, they're saying don't do it because this integral might be 20 pi in the end. If you calculate everything, might become 20 pi or 2 pi, whatever. But yeah, they're saying just don't. They wanted to see the 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 limits of integration and everything that you've got. But also the fact that when we're starting cylindrical coordinates, is r dz dr d theta for the triple integral. R dz dr d theta means cylindrical coordinates volume. Okay, so it's something that you need to take note of. And then we move on to the next question. Yeah. Okay, so we have done that one. Let's just look at the next question, question 5. Question 5. Can you see? Let V be the plane perpendicular to the vector 2, 2, 1 and containing the point 0, 0, 2. There is a plane perpendicular to the vector 2, 2, 1 and containing the point 0, 0, 2. Let S be that part of V in the first octant. In the first octant. That is where X is greater or equal to 0, Y is greater or equal to 0, and Z is greater or equal to 0. Find an equation for V. Find an equation for V. Find an equation for V. Let us do this one. So the question is, what do we do in a situation like this, and how do we actually answer this particular question? Right, how do we answer this particular question? So we proceed as follows. Right, we proceed as follows. We proceed as follows. Right, so there are a couple of things that we need to take into account here in terms of how we find an equation for V, the plane. In terms of how we find an equation for V, the plane. Right, so we can be able to find an equation for V, the plane, but we look at actually how we actually can be in a position to find an equation for V, the plane. So now, this is how we find an equation for the plane. Right, so we're doing 5.1. So we can start by saying there's a point XYZ minus another point. There's a point. So this is 0, 0, 2. Then you take it, you dot it with a vector. 2, 2, 1. And this is equal to 0. XYZ minus 2.
Sorry, I didn't get. Why are you doing what are you doing now?
Okay, we want to find the equation for the plane. One way, if ever you let V be the plane perpendicular to the point, so there's a plane like this that is perpendicular to the vector. So this plane is perpendicular to the vector. And this vector is 2, 2, 1. So there's a plane such that is perpendicular to this vector. And this plane is containing the point 0, 0, 2. So let S be part of V in the first octant, where first octant means that you are dealing with like a quadrant. A quadrant is 4, octant is 8. So which means that when you're dealing with the first octant, you are dealing with the 8 regions. The 8 regions of the 3D space. Right, the 8 regions of the 3D space. There are 8 regions of the 3D space. So that then in the end, we have the following. In the end, you have exactly the following. Now, this one is a, is a, is, a, is, 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 is called an octant. Octant has to do with the eight regions that you are able to get here in the 3D plane. 3D plane. 3D, you can normally call it a 3D space. Right. So if ever you have this, so you have been given this. This is the plane V, and the properties that are given with it. So you take a point XYZ minus another point. So this XYZ is just some points, arbitrary point, right? It's some arbitrary point on the plane. So you take the 2 points, and this one is, say, suppose here. And then now you take this one minus this one, you dot it with 2 to 1, and therefore, because the 2 to 1 is perpendicular to the plane, then this and that are orthogonal. They're orthogonal vectors. How do we know they're orthogonal vectors? Because you have the XYZ plane together with the 002 plane. Now, these ones are on the plane, but if you subtract them, you get a vector on the plane. Subtracting them produces a vector on the plane. Right. If it produces a vector on the plane, then you dot it with 2 to 1. The result is 0, which is this. You dot it with 2 to 1. And if you dot it, the result is 0. Why is the dot product 0? Because the plane is perpendicular to this 2 to 1 vector. The 2 to 1 vector is some normal. It's some normal. It's a normal, which is a perpendicular vector. Okay. So now we're going to do component-wise multiplication, which means x by 2, which is 2x, 2y, z minus 2, 0, which means 2x plus 2y plus z equals 2. Okay, you can write it like that, but you can also leave it. You can leave it this way. We found the equation of this plane. We found the equation of this particular plane. But it's not the only way to find the equation of the plane. How else can you find the equation of the plane? We can find the equation of the plane like this, or we can use our old techniques. What are the techniques? We can use vector x dot normal is p dot n, which is x, y, z. The normal is 2, 2, 1. The point is 0, 0, 2, and then the normal is the perpendicular, which is the same as this, 2, 2, 1. Which means you have 2x, 2y plus z, which is equal to this by that 0, this by that 0, giving us 2. Which means 2x plus 2y plus z minus 2 equals 0, which is the equation of the plane. So the red equation is the same as the green one. So we can use the top method, or we can use this bottom method to find the equation of a plane. So we can use x dot n equals p dot n, or we can use this one to find the equation of a plane. Any question about finding an equation for V, the plane?
No.
Okay, good. Now we move to the next question. Now we need to sketch S. Sketch S and its XY projection. Now we're going to be looking at the projections and XY projections of the sketch. Let's analyze this and focus on the XY projection. Now, obviously, now you let S be part of V in the first octant. Right, in the first octant. So we note that in particular, S is the shaded. Is the shaded triangle. Given below. So Z, Y, X. Okay, this is our 3D space. And if we're going to look at the plane we've got in the previous question, we've got this plane. 2x plus 2y plus z minus 2 equals 0. We repeat, 2x plus 2y plus z minus 2 equals 0. So that's what you're going to write. So you're going to write 2x plus 2y plus z minus 2 equals 0. Let us be part of the plane in the first octant. So we want to sketch this one, the first octant. The first octant, it is where y is greater or equal to 0. Yeah. X is greater or equal to 0. Z is greater or equal to 0. If we are in the xy plane, then we then say z equals 0. If x and y are 0, then you have 0 plus 0 plus z minus 2 equals 0, which means that z equals 2. So you're going to have, for instance, z equals 2. And then now you come to another situation where x is 0, z is 0, then you're going to have 2y. X is 0, so it's 2 plus 0 plus 2y plus 0 minus 2 equals 0, which means y is equal to 1. So this one is going to cut at 1. You continue. Y is 0, z is 0, which means 2x 0, 0 minus 2, which means x is 1. So now you're going to have x equal to what? X equal to 1. And then let us sketch this in the first octant. This becomes the first octant. So this one is going to be like this. This is going to be this way. Okay, let us draw carefully. So which means you're going to have exactly this one. And then this one. 1, 1, 1, 2. Like this. And then we need to shade. That's all. So now sketch S in the X in its XY projection. Okay, this one is the set S. Then we continue to look at the XY projection. You continue to look at the XY projection. The XY projection of this triangle. Right, of this triangle is the following. Is the following triangle. Which means you have this. Which means the XY projection now you're going to be looking at what happens here. So on the XY plane, then you can see that X is cutting at 1, Y at 1, and therefore this is the projection. This becomes the XY projection. Right. So now the XY projection of this triangle is the following triangle. Right, because now if you just only take the what is happening in the XY plane, then this is what you're going to get. This is what you're going to achieve. Okay. So now we have done the XY projection. Which is just the image of this, or the shadow of this in the XY plane. The shadow of that in the XY plane. Now we are done. Determine the downward flux of F through S, where F is a field, a vector field. So F is actually what you call a vector field. And then we need to just determine the downward flux of F. To determine the downward flux of F, there are a couple of things we need to take into account. Right, what exactly do we need to take into account here? Right, we need to look at the fact that we are actually in a position to consider every single bit of thing we need. Every single bit of thing we need. Right, every single bit of thing we need. Let us look at 5.3, which is this one. Determine the downward flux of F through S. Right, 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 right. Right. So the question is, what do we have here? What do we have here? Okay, let us determine the downward flux together. How do we find the downward flux? That is the question. How do we determine the downward flux of a vector field? How do we find the downward flux of a vector field? Right, so we continue.
Yes.
Okay, we continue. Now, to find the downward flux, we need to first consider the normal. So we then say first the normal. The normal to S, because S is what? Let S be part of the plane in the first octant. So the normal to S is the unit vector. Is the unit vector in the direction. Is the unit vector in the direction 2, yeah, okay. And then you have -2, -2, -1. We're saying the normal to S is the unit vector in the direction this. That will be a normal to S. Because if you're then saying V be the plane perpendicular to this one, right, and if it's a vector perpendicular to these, then the normal to S which is, now S is this one. S is actually this first octant, this particular part of the plane in the first octant. Right, and then we proceed obviously to shade it. We proceed to shade it, and this one is our ZYX. So the normal to S is the unit vector in the direction. The length of this vector so now the length of this vector is the square root. Right, so the length of, so now we're saying the normal to S is the unit vector in that direction. Right, it's the unit vector in the opposite direction to this, because this is 2 to 1, and therefore normal to S is the unit vector in the opposite direction to this. Opposite to 2 to 1, you multiply 2 to 1 by negative, and then you have this one. So that the normal of this vector becomes the following. Minus 2 squared. Minus 2 squared. And then you have 3. You have 3. The length of this vector, I mean, take its magnitude, you get that. This would therefore mean, right, it therefore means the normal vector, you divide by the length. So it's going to be 1/3. It's going to be 1/3 of minus 2, minus 2, minus 1. So that you have F dot N. And then now if you have F dot N, you want to find the outward flux. Right, so you dot this one with the vector field. And now you can take out the 1/3 as a common factor, and then dot the vector field is X plus Z together with the Y minus Z and also with Z. You dot it with this one minus 2, minus 2, minus 1. So you have 1/3. So now what actually we are able to achieve here becomes exactly the following. You dot this and that. It becomes minus 2x minus 2z. You dot this and that, which is minus 2y plus 2z minus z. 1/3 of the following, minus 2x minus 2y minus z. Because now when you have the minus 2y and the minus 2x are the minus 2z plus 2z is 0, which gives us minus z. Now for the downward flux, you need to note that this is the first octant. This is in the first octant, where first octant would mean x positive, y greater or equal to 0, also z greater or equal to 0. But you need to think about this and realize that if we're speaking about the word downward flux, you need a vector that's going to point down. So if you look at the vector 2, 2, 1, where x is 2, so the vector 2, 2, 1, x, y, z. So you have x is 2, y is 2, z is 1. And therefore, you would do this. X is 2, you do this. Y is 2, you do this. X is 2, you do this. So this point in the xy plane, it's going to become what? Right. 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 So that this is 2, 2, 0. When you are here. And then now you're going to look at this one. So this one, so you're going to come here and the point that is here would be having the coordinates 2, 2, 1. 2, 2, 1. Then you need a downward one. So this one is going to be coming from the origin to this. But now, if this is the case, then you want it to go down. So you're going to look at what is going to happen in the opposite direction. This is like going up and then it's going down. Going down, this one is the -2, -2, -1. And this is why we're saying the normal to S is the unit vector in this direction. So we're looking at the negative vector there, which is in the downward direction to this there in the first octant. Right. 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 So we continue. We continue.
Yes.
Okay, right. Now to find the downward flux, you take the vector field dot the normal. That is the formula. So it is 1/3. We've already got that one, and we got minus 2x. We got minus 2y minus z, like so. The next thing we're going to do is to find the vector ds, which is the square root. dz dx, which is dz dy. This is the formula that we use. dA for the flux. We use this formula for the flux. Right. So we continue.
Yes.
Right. So now at this point, this is the formula we use for the flux. But now we find the ds as it is there in the study guide. But we need to find our dz dx. And the dz dx becomes exactly the following, right? So we got our z before, And you would remember that we got 2x for the plane, 2x plus the equation for v, 2x plus 2y plus z minus 2 equals what? Equals 0. Now, with this, what will z be? Z will be the same as, for example, um, minus 2x minus 2y plus 2. And then we have dz dx, which is minus 2. And then dz dy. So we're getting dz dx, which is minus 2 for dz dx, minus 2. Then we find that the partial derivative of z with respect to y is minus 2.
Sorry,
Yes, please.
I asked why are we using minus, like why did we change the signs for x and y to negative?
Here in this equation, because we want to make z the subject. Because of the equation we use for the flux, it is the dz, the x. So we must make a z the subject so that we can be able to find the derivative of z with respect to x partially, but the partial derivative of z with respect to y as well. So that now, with this, just transposing the terms, making z the subject so that we can be able to find the derivatives. Okay. At this point, we proceed to say ds. So this one is minus 2, you square it. The dz dy is minus 2, you square it, plus 1 dA, which means that you shall have ds is the square root. 4 plus 4 plus 1 dA, which implies that ds for the flux is 4 plus 4, which is 8, plus 1, which is 9 dA. Square root of 9 is what? Is 3 dA. Square root of 9 is 3. So now we've got another equation that we need to use. But we're not done yet because we want to find the downward flux, and we proceed as follows. There's something we can do right now, and we are effectively then saying now we can calculate. We can calculate the flux by converting. By converting the surface. Right, the flux they want by converting the surface integral. Right, the surface integral to an ordinary integral. To an ordinary integral. Right, to an ordinary double integral over the region R. The XY projection, right, because now we dealt with the XY projection before for this region interface octant. So we are moreover saying the XY projection. Right, so the XY projection drawn in 5B It is described in Cartesian coordinates as. So now we can calculate the flux by converting the surface integral to an ordinary double integral over R. The XY projection drawn in 5b. Right, so we looked at the XY projection, which was this. Obviously, the X has both 1, 1. We saw that before. We saw that before. Right. So that R, the region. Right. So this one, you can write it as R. Right. And then now, if you have the R, then it can be written as R. And we have exactly the following. Right. We have exactly the following. So okay, you can write it as R equals XY. And this would be 0 is less or equal to X less or equal to 1. Y is, you see, X is this one. So X is between 0 and 1, but also Y is between 0 and 1. But why we can find the equation of this? Because if you find the equation of this, how to find the equation of a line? You use Y minus Y1 equals M into, in brackets, X minus X1. So now what you do is you find the gradient of this. So the gradient of a line is change in Y, change in X. This point has the coordinates 1 and 0. This one, 0 and 1. Which means Y2 minus Y1, X2 minus X1. X1, Y1, X2, Y2. Y2 is 0, Y1 is 1 divided by X2 is 1, X1 is 0, which is minus 1. So that is the slope. But this line passes through one of the points. Maybe you can take 0, 1. And if we take one of the points, we can be in a position to find the equation. We want to find the equation of this line. So which means that you're going to have Y minus, this is X1, Y1. So that Y1 is 1. The slope is negative 1, X minus 0, which means that you have Y equals minus X plus 1. This is the equation of the line. Or you can write it as 1 minus X. So that the Y is also 1 minus X. Okay. And then you close like this. We compute. Want to compute the following. One, 1. One minus X is the equation of this line. And so now if we want to compute the, so we compute the downward.
Bobby,
Yes, please.
I think you wrote for the region, ne,
Yes.
concerning the y interval, you said 0 is less than y, and is less than y minus x squared instead of x.
Where? Which one?
There, like where you said 0 is less than y is less than 1 minus x squared. I thought it was going to be 1 minus x.
Yes, it is 1 minus x. Is it a square? Did I use a square somewhere?
Is that another 2
2. Oh, this one.
on the interval, like the
This
region?
one. This one.
Yeah.
Yes, because x is between 0 and 1, right? Because this is 1. X is between 0 and 1. But y is between what? Because if x is between 0 and 1, so what you do is, I'm trying to get your thoughts. 0 to 1. So this is x. So what you do is, or you shade this. X is between 0 and 1. But y will be between 0 because y is 0 here. You
Oh,
drop.
I see. It's your Celt bracket that confused me.
Oh,
I thought you were
yeah,
square.
that's what I was thinking. But I was just like, again, I thought the curly bracket is clear enough. Okay, so it is a bracket like this. Okay, sorry, you thought it's a square. My apologies. Okay, good. So now we have this. Right, so we compute the downward flux of F through S. So we continue. So now
Yes.
this downward flux becomes the formula for it is the double integral of F dot N ds is the double integral over the region R. And now the F dot, right, so we go back to this. We go back. The F dot N is 1/3. Right, it is 1/3 of minus 2x minus 2y minus z. 1/3 of minus 2x minus 2y minus z. This ds, what is ds? ds is 3dA according to this formula. It became 3dA. ds is 3dA. So wherever ds appears, we're going to put 3dA. So wherever ds appears, we're going to put 3dA. Meaning this 3 is going to cancel this one. For the outward flux, we found the double integral over the region R minus 2x minus 2y minus z dA, which means we have the double integral from 0 to 1, from 0 to x. Right, we have exactly this here. So these would therefore be the same as the following. So this dA becomes dy dx. X is between 0 and 1, but y is between 0 and 1 minus x. Okay. And then now we have the minus 2x, the minus 2y, the minus z. Right. And so we analyze this very, very carefully. And we're able to take note of the fact that this would become the following. Because the plane, the equation for the plane V is given by what? We got 2x in the beginning. We got 2x plus 2y, but we also had plus z minus 2 equals 0. And then we transpose everything, moving all these things to the other side with minus 2x minus 2x minus 2y minus 2z minus z is minus 2, like this. Okay, so here, all these things, minus 2x minus 2y minus z is equal to minus 2, because that is the equation for the plane V. Okay. Now let us do some integration here. So it means the integral of these is the integral from 0 to 1. But the integral of minus 2 is going to become minus 2y 0 to 1 minus x dx.
So, why did we ignore the equation? Yeah, the one that you're pointing at now.
Okay, good. Why did we ignore this equation? Well, that's interesting, but we did not ignore it. What we did was, we already know the equation for the plane V. What is the equation for the plane V? We got it in 5.1. It was 2x plus 2y plus z minus 2 equals 0. Now, we want to simplify the integrand here. So to simplify this integrand, we can, this one, the 2x, the 2y, and the z, we can move them across the equal sign. So 2x becomes negative. 2y becomes negative. Z becomes negative. So it means that we would have 2x minus 2y minus 2z is equal to, minus 2x minus 2y minus z is equal to negative 2. So which means this minus 2x minus 2y minus z is all equal to negative 2, according to the equation of the plane in 5.1. Okay. Now, with this, we are able to do the following. We are able to do the following so that we can integrate here, this one. Right. So if we integrate these, we'd get the following. Would get exactly the following. Would get exactly the following. Right, let us integrate together. Right, okay. So we integrate from 0 to 1. So it's minus 2, and then you substitute everything. You substitute the 1 minus x and then minus 0 dx. And then if you simplify this one, it becomes the integral from 0 to 1. We have minus 2 plus 2x dx. Right. So it's minus 2x plus x squared from 0 to 1, which is minus 2, 1 plus 1 squared minus 0. And therefore, this is minus 2 plus 1, which is minus 1. And this is the answer. So we have to find the downward flux. So we change the vector 2 to 1 to minus 2 minus 2 minus 1 for the direction downward. But this has meant a couple of things, but it has meant that we can actually be rest assured that at any rate, we have exactly the following. We have exactly the following. Right, it is clear that we can know that the downward flux, which is the integral over the surface S of F dot NdS, this integral is -1, so that the downward flux of F through S is -1. This is it. This is it exactly. And so we've solved the question 5.3. We have solved the question 5.3. Okay, now the couple of things we need to take into account here. But it is the next question. Right, it is exactly the next question. Right, it is the next question. The next question is question 6. Consider the R2 to R function defined by this. Find the critical points of F and determine their nature. Right, so we have this one. We want to find the critical points of F, but also we shall find their nature. The question is, where do we start? And how do we proceed with solving this particular problem here? Right, how do we proceed with solving this particular problem here? Right, so we will proceed as follows.
May I suggest we skip this one?
Okay, you think it's too easy?
Yes.
Okay, good, that's fine. Because if it is too easy, then I'll have to obviously accept your assertion, because that is what you think is the right thing to do. There are a couple of other problems, obviously. There are too many problems. Some of them will give them to you as homework. Let's look at the next one. The next one is 7, the method of Lagrange. Use the method of Lagrange to determine the what? The radius and height. The radius and height of a cylindrical tank. Right. That will have the maximum volume subject to the constraint that the area of its outer surface, and the outer surface means the top and bottom included. So in other words, this one here is not just a cylindrical tank, but it has a lid, but also it is sealed at the bottom so that you do not have any leaks. Nothing is leaking there. Nothing is leaking there. Right, so this is something very, very important. So now you realize that you have absolutely no leaks. But this area of its surface, the top and bottom included, must be 600 pi square meters. 600 pi square meters. Right, 600 pi square meters. Let us reason this together. We need to get our 10 marks. This question is very much examinable. We need to master the method of Lagrange like yesterday. And we can't delay its analysis. Let us tackle this question with much zest and a very high degree of confidence, and do number crunching on it, and be able to solve this particular problem in detail. We start as follows. Right, to use the method of Lagrange to solve the problem, we actually need to take note of the following. We minimize, right? Because we want to be in a position to remember if we want to actually have the maximum volume, right? If we will have the maximum volume, there are instances where we're gonna obviously maximize, right? So we'll say we maximize, in fact, for a start. Right, we maximize. We maximize the function. Right, we maximize the function g, rh, which is pi, r squared h, subject.
Can you please I've tried this before, but I don't understand what exactly does Lagrange method actually like entails. Like every time
Well,
I come up with a
yes, we
Lagrange
shall. Yes,
question, I'm
we shall summarize the method. But the method of Lagrange requires two functions. You require two functions, and with the two functions, you will actually take the two functions and do what? And use the formula for the method of Lagrange. What is the formula for the method of Lagrange? This is the method of Lagrange. The method of Lagrange says the following. Method of Lagrange. The method of Lagrange means that there is a constraint condition. So you find a gradient of the constraint. So there will always be a function that is going to equal a constant, and that we call g. And then we take lambda multiplied by the gradient of another function we call f. So now this is the method of Lagrange. So this one is called the constraint. So you're going to establish a function g, which is the constraint, and then the function who's that we need to um, um, minimize or maximize, whatever is necessary. Okay, right. So at this point, we need to we maximize the function g, right, subject to the constraint. Right, subject to the constraint. F. HR. And this becomes, if you have the thing, this cylinder, it has a lead at the top and at the bottom, yeah? So you have something like this for the um cylinder, huh?
did you
So you'd
is
have
it can you please sorry,
yes,
can you please clarify, is it f function of h comma r
we can
or l? Like I don't understand.
okay, good. Let me just be consistent. Doesn't matter because these are dummy symbols. It's RH. Let's keep them the same. Right. So this would be what? Would be the lead because the lead is like a circle. So it's pi r squared and this one is also pi r squared. So now you add pi r squared plus pi r squared, you get 2 of the pi r squared. But now this lead, you can open it. This cylinder, you can open it like this. When you open it like this, then you'll find the circumference of it because if you If you fold it a little bit, whatever to form the cylindrical the side, vertical side of the cylinder, this one becomes what you call the circumference of a circle, which is 2 pi radius. But obviously, this particular tank has a height h. So the area of this is length by breadth. Length by breadth is 2 pi r h. 2 pi r h. Right. So it is exactly 2 pi r h. So if it is exactly 2 pi r h, then you would actually be in a position to get the following. So now you'd have, we can take, right, right. We continue.
Yes.
Okay, we continue. Okay, so you can pull out a common factor from this, because now we have dealt with the top and the bottom, the lead and the base, and then we dealt with the side material, and then this is forms a rectangle. If you cut the tank open, and this forms a rectangle, which is the vertical section of the tank. But if you take 2 pi r as a common factor, you have r plus h. But Um, we want to use the method of Lagrange to determine the radius and height of the cylindrical tank that will have maximum volume, subject to the constraint that the area of the outer surface must be this. The area of the outer surface. So the area of the outer surface will be the area of the top, which is pi r squared, the area of the bottom pi r squared, which is 2 pi r squared, then the area of the side. But the area of the outer surface is 600 pi square meters. So it's 600 pi square meters. So now let's do this. Okay, we're here to summarize. I was just writing the method of Lagrange that we're going to use, but we are in business now, because I'm sure that everything is pretty clear. Maybe I shouldn't have erased this, but it's okay. We have seen it already. Now I want us to the gradient. GRH. Right, the gradient of GRH. We find the gradient of this. The gradient, like I said, is going to be GR, then GH. Partial derivatives, right? So the derivative of this one with respect to R, which is R squared with respect to R, is going to be 2 pi RH. 2 pi RH. The derivative of this one with respect to H is pi R squared. Which is FRH. We find the gradient of FRH, which is FR FH. Okay, F is this one, which is this. But we want to find its derivative, right? Its gradient. And then now we're going to find the partial derivative of F with respect to R. So with respect to R of this one is going to be 2 pi R. This one, yeah, okay, 2 pi R plus, it's going to be 4 pi R. Because if you find the derivative of R squared is 2R times 2 pi is then 4 pi R. The derivative of the partial derivative of 2 pi R with respect to R is going to be 2 pi H. The partial derivative of this one with respect to H, this is 0 and this is 2 pi R. If we do this, then we continue to use the method of Lagrange. Now, right, so now we have the following. Now, Lagrange's method. Lagrange's method requires that we solve, right? By method of Lagrange, you need to solve the gradient. The F is a constraint. So which means that we're going to be want to find the maximum volume subject to the constraint. So the maximum volume, this is what we want to find. So which means that the gradient of G is lambda, the gradient of F. So we continue.
Yes.
Okay, this one is a method of Lagrange, this, because we want to optimize this gradient of G and then lambda gradient of F. Therefore, when we're dealing with the gradient of G, which is lambda, the gradient of F, but GRH is the, right, G is pi r squared H, which is like volume, because the can that is given like this, the tank that is given like this, the base is a circle, pi r squared times the height, FRH, 2 pi r squared, 2 pi RH, the gradient of G. We have already got it. What is the gradient of G? Right, the gradient of G is GRH is 2 pi RH, 2 pi RH, then pi r squared. 2 pi RH, pi r squared. Lambda. The gradient of F, which is 4 pi r plus 2 pi h plus, and the 2 pi r. So which means the gradient of F, 4 pi r, 2 pi h, 2 pi r. Okay, now let us look at the next thing. 2 pi RH is lambda. Now this lambda, good. This lambda is going to be multiplying the first component. So it's 4 pi r plus 2 pi h. Okay, so you do that one and welcome Pegelelo. 4 pi r squared is lambda 2 pi r. So the first component we equated to the first, and the second component is equated to the second component, just likewise. So at this point, we have exactly that. Hence, we divide through by 2 pi r. Okay, the r is not there, so you can just divide by 2 pi. So if you divide by 2 pi by 2 pi by 2 pi, it means that the 2 pi is going to disappear. It's going to give us RH equals lambda. You divide this one by 2 pi, it's going to be 2r. And divide by 2 pi, this one is going to be exactly h. Okay. And You divide this one by whatever becomes a common factor. You divide by pi r, which is exactly the same as what? Which is exactly the same as r is equal to 2 lambda. You divide by pi r. This is what we get. And if we can do this, and then we can see that, and consequently, right, and consequently, 2 lambda h, right, and consequently 2 lambda h is actually lambda 4 lambda plus h. So, in other words, you come to this formula. Wherever r appears, we can put 2 lambda. So there's r here, we put 2 lambda, but there's h, there's 2 lambda h. But there's r inside, and then we put 2 lambda, and then 2 times 2 lambda is 4 lambda, plus h, and then the lambda is outside. So we have put this r in 2 places. So it means that we've put this r in the places for r. Like we've put it there, and we put it there, like that. Okay, think about this. Think about this. By substitution, I've already done, or obviously possibilities in this direction than the opposite. So that now, what is this? 2 lambda h is 4 lambda squared plus lambda h, which is 4 lambda squared minus 2 lambda h plus lambda h equals 0. Okay? Right, we apologize to lose you there, Pehelelo. So that 4 lambda squared. Now, this minus 2 lambda h plus lambda h is minus lambda h equals 0. Lambda is a common factor out of these, giving us 4 lambda minus h equals 0. So that we have lambda, 4 lambda minus h equals 0. Thus, from this, we're able to see that lambda is equal to 0, but also lambda becomes h out of 4. As lambda is equal to 0 is not possible. Lambda equal to 0 is not possible. Right, it's not possible. We see that. Right, we see that. We see that lambda is h over 4, but this becomes exactly r over 2. And where we used equation 1. So now, if you cross multiply everything, this 2, this 4, you cross multiply this one, making h the subject, it's going to be 4r over 2. And if it's 4r, 4 divided by 2, it's 2. But it's r there. Okay, so this produces another equation. But we're not done yet, because there's another fact we need to use? Using the fact that FHR is 2 pi r squared 2 pi r h, which is 2 pi r plus h. Okay, we got f to be like this. Why is f like this? Because we're dealing with a tank that is cylindrical. The top is a circle. The area of a circle is pi r squared. And then we saw that if you open it, it's going to be like a rectangle. But this has height, and the circumference is 2 pi r. And we know that the area of a rectangle is length by breadth. Length by breadth. Length by breadth. Okay. Right. So that in the end, you have the following. Right. So that now you have 2 pi r. But now you know that wherever there's h, you can put 2r into this, which means you have 2 pi r, and then you have r plus the h becomes 2r, which equals 600 pi. We multiply everything here. So what we're having here right now is that r plus 2r is 3r. But 2 times 3 is 6 pi r squared, which is equal to 600 pi. Okay, so dealing with cylinders, we divide through by 6. And then we divide through, so this one is going to be 6 pi. R squared is 600 pi, and then you divide by 6 pi, 6 pi. Right, which means that it is exactly 100. You have this one, so R, the square root of 100 is 10. This has given us R equals 10, yet H is 2R. H is 2R, which means R is 10. 2 times 10 is 20. So now, obviously, you see, we're determining the radius and height of a cylindrical tank that will have the maximum volume subject to the constraints. Right, the constraint that the area of its outer surface, top and bottom included, must be exactly 600 pi square meters. And this is the answer. So at this point, we've got that R is exactly 10, and H, which is the height of this cylindrical tank, the height is 20. The height is 20. Any question about the method of Lagrange? And these obviously is what the method of Lagrange entails in detail. Any question, any input, and any thought? We have taken basically 3 slides to do this, or 3 boards. Right. We started by converting the words into mathematical equations, and we're successful. But the method of Lagrange is that the gradient of G, with which G must be maximized, and then it is lambda times the lambda times the gradient of F. F is the constraint, because F is 600 pi is a condition that F is a constant, and then we were able to get the answer. Any question on this?
No.
All right, yeah, think about it and make sure you understand. It was awesome having this discussion today. What is your homework? This is your homework. This becomes your homework. 11 marks. Let
Can you please send the homework
recording
on WhatsApp? Yeah. No, the homework.
Okay, good. Yeah, I'll send it on WhatsApp. Okay. I'll
Bye.
mostly send it
Thanks.
on WhatsApp. Okay, thanks a lot. It was awesome having this discussion. Yeah, we're not done because now there's another class that is starting. So that will be after 10 that I will do those things because now I have some school kids who actually want to learn something until 10 o'clock. Okay, right. Thank you so much. Goodbye. So now I have Pegelelo here and Zote. Zote, why don't you register? Zote. Zote. Zote, why don't you register? Zote. Zote, why don't you register? We've been waiting for you to register, Zote. You are busy playing there. What is the problem? Okay, we're starting now, Pegelelo. There are too many things I want to discuss today. Right, there are too many things we want to discuss. Zote, why don't you register? Because you don't want to register. And you are busy playing. What is the problem? You don't want to register, Zote. All right, so right. Right now, we want to practice more mathematics.